first order circuits, we have been dealing with nonlinear, piecewise linear, nonlinear circuits, and we have first looked at a circuit where that piecewise linear circuit is constructed with an operational amplifier with these three branches, where it's modeled as a nullar, or we have the positive or the negative saturation voltage, and with the three resistances we basically get these S-type shaped nonlinear resistive characteristic. And by connecting a capacitor across the terminals of this nonlinear one port, we observe an interesting phenomenon which we call the jump phenomenon. So when we start out with an initial value of the capacitor voltage in this point P0 here, so it's this initial voltage for that capacitor here, and look at the dynamic route in which direction the voltage will change, we observe that due to the negative current, we observe that due to the negative current, the derivative, there should be a dot, the derivative of the voltage should be positive, and therefore we move towards these point Q1 or P1 here, where we observe that this is an impasse point. So there is no solution there, and the only thing we can think of as a heuristic solution is to look, is there somewhere on that VI characteristic, is there a point to which we can go to without violating the law that the voltage across a capacitor should be continuous, and where we avoid this impasse situation. And we find that this is valid in point P2, and here we have then an evolution over time towards P3, and here we have the same impasse point problem and the jump to P4, and this goes on, and on this parallelogram the state of the circuit moves on and on forever, as long as we not disconnect the operational amplifier from the power supply. And this is a relaxation oscillator or a multi-vibrator. And then we have seen, in addition, if we interchange the polarity of the inverting and the non-inverting input of the op-amp, then the behavior of the circuit completely changes. It's not an oscillator anymore, but it's simply a flip-flop, a storage element where we can store information. That was basically the end of the chapter on first-order circuits, and then we went on looking into second-order circuits and started our investigation with a simple example circuit where we have two storage elements, two reactances, one capacitance, one inductance, and have first been writing down Kirchhoff's equations for the node in green color, for the loop in blue color, then the equations connecting together voltages and currents and derivatives thereof across the elements, and putting that together into two coupled linear first-order ordinary differential equations, which we then have been writing down in vector matrix form. So the nice and really compact and efficient way to describe such a system is to put these two state variables, in this case it's the voltage across the capacitor and the current through the inductor, pull them together into one two-dimensional vector x, where we have the two state variables. If we take the derivative of the vector, and remember, taking the derivative of a vector is applying the differential operator to the individual elements of the vector, then we can write the whole system of equations in this way that we have simply the same equation as we have seen from the first-order circuits, by simply replacing that it's not one state variable, but it's a vector of state variables. And that goes on for arbitrary dimension. and the coefficients, the constant coefficients now are not scalars but matrices. That's the only difference. Briefly, I've also shown you that one could compact these two coupled equations into one uncoupled, it's only one equation, but then we have higher order derivatives to take care for. Okay. Ja, soviel dazu, und heute wollen wir jetzt uns einen formalistisch gestalteten Weg anschauen, wie man auf jeden Fall zu diesen Zustandsgleichungen kommt. Und dazu machen wir das Gleiche, was wir schon bei den Schaltungen ersten Grades gemacht haben. Wir trennen einfach den resistiven Teil und die Reaktanzen. Beim Grad 1 hatten wir ein resistives Eintor und eine Reaktanz, die mit diesem Eintor zusammengeschalten wird. Hier brauchen wir jetzt ein resistives Zweitor und zwei Reaktanzen, die wir an die beiden Tore des resistiven Eintores eben anschalten. Und dann denke ich mal hier